So good evening, everyone, and I welcome you all to today's live session. So today we have an extra session for the course Nonlinear Vibration, NOC25 me57. We have already completed 12 live sessions for this course for the 12 weeks, and we have discussed about questions related to nonlinear vibration and whatever was taught in the course, so that it will be helpful for you to get into the deeper insights of the course. Okay, so today is an extra session where I'll be discussing about the overview and the broader prospects of nonlinear vibration. And if in case you have any doubt, you can ask me. So I'm Rashi Aditi Ranjan, NPTEL PMRF TA, the Department of Mechanical Engineering, IIT Patna. So we'll start our discussion with what we have been doing since the last 12 weeks. So, as we have already discussed many times, that while dealing with a nonlinear system, the biggest challenge is to know how the system is going to behave, right? Because for a linear system, if I have an ordinary differential equation, or even if I have a partial differential equation, it is easy for me to solve the equation because then I can get a closed form solution. And if I have a closed form solution, I can know how my system is going to behave under what conditions, right? And apart from that, usually the relation between the input and output is monotonic since the equation is linear. So either with the increase of the parameter, the system is going to show increment in the response or it is going to show decrement in the response. However, it is going to be a monotonic function. But in case of a nonlinear system, that is not true because nonlinearities are present in the system, and because of the presence of those nonlinearities, the monotonic relation does not exist. Okay, there's a non-monotonic relation. But what is going to be the relation that we don't know? Now, either what we can do is we can study it experimentally and then we'll get to know that, okay, this are the prospects of the system. But if you see, there are various parameters where environmental conditions and everything that contributes towards deciding how the system is going to behave. So for a nonlinear system, it becomes difficult. Now, the best way, like we have been dealing with any of the linear equation, is that we get the equation of motion and then we find the solution. So for getting the equation of motion for a nonlinear system, what are the possible ways? So these are the possible ways. Okay, so we have a lumped parameter model and a distributed mass model. For a lumped parameter model, we mean that we take a system and we divide it into some n number of lumped masses, spring and dashpot. And using that, then we derive the equation of motion. So it has, finite number of masses, finite number of spring and finite number of dashpot. And so there is a finite number of natural frequency in the system. Okay. But in case of a distributed mass model, we consider our system as a continuous uh, system, right? Wherein we consider the mass is distributed continuously, uniformly, and then we derive the equation of motion. So when we are working with a distributed mass model, usually we have infinite number of natural frequencies. Okay, so anyways, we can model a continuous system as a lumped parameter model or as a distributed mass model. It depends only and only on us that how and in what way my system is working. Okay, so it depends upon what are the application of the system, how the system is working, what is the final result that we are expecting from the system, and then we can choose whether we should work with a lumped parameter model or the distributed mass model. Usually, when we require the application of my system for not so accurate dynamics. Like for example, I want it to be used as a ceiling fan, or I want it to use as some other thing which does not which is not where I don't require that much of precision and accuracy. I can use the lump parameter model. But when I go into complicated dynamics, like for example the design of an aircraft, wherein there are very high amount of contributing factors that affect the movement of an aircraft and the safety of an aircraft, that time using a distributed mass model is very important, and that time accuracy is all and precision also plays a very important role. Okay, apart from that, equation of motion may be also derived by getting the either the force balance method or by using the energy prospect of the system. So when we are using the force balance, we can derive the equation of motion by the Newton's second law or by the D'Alembert's principle. However, if I'm using the energy prospect, then I can use the Lagrange or the extended Hamiltonian principle. Anyways, we have a Lagrange equation and a Hamiltonian principle, which is applicable for a system which does not have any kind of a dissipation, or we say for a conservative system, while an extension of both these ways of finding the equation of motion has been given in order to get or in order to incorporate the effect of dissipation or the non-conservative forces that are present in the system, and then that is known as the modified Lagrange equation and the extended Hamiltonian principle. Modified. Okay. Now, now the most important thing is, okay, I'm done with finding out the equation of motion. But how will I know whether my equation of motion is actually non-linear or not? Okay. If I am starting from the very basic, I don't know how to identify whether my system is non-linear or not, right? So in that case, what do? I use the superposition rule to find out whether my equation of motion is non-linear or linear. Okay. So if you remember, in the superposition rule, we basically studied two ways. One was the homogeneity rule, and second one was the additive rule, wherein we had to check, like for example, for the homogeneity rule, if I am replacing x with alpha x, so my function should be alpha f, right? And for the additive rule, it was like if I'm replacing my alpha x, sorry, okay, I'm audible. Okay, so coming on to the additive rule, so if I replace my x with x1 plus x2, then my function, it should be something like f1 plus f2 should be like f of x1 plus x2. It should be something like this. The additive rule should be applied and the homogeneity rule should be applied. And if this happens, then we say that, okay, our system satisfies the superposition rule and hence it's a linear system. While if it does not satisfy the superposition rule, then my system is essentially a non-linear system. Okay, I hope this is clear. This is the very basic way of basically identifying whether my system is linear or non-linear. But once I keep on doing this practice, then it becomes easier for me to just look into the equation and then I can just say whether my equation is linear or non-linear. Now, then we come on to the stability analysis, wherein we were discussing about the static characteristics of the system. So it was like, though my system is non-linear, it is definitely going to have some equilibrium points. Out of them, some could be stable, some could be unstable, right? Some could be like center or whatever the possible cases are. So if I want to know what are the stability characteristics of my system, what will I do? Now, when we talk about the stability analysis of a nonlinear system, there is no particular dedicated theory or rule that applies for a nonlinear system. Okay, that okay, if this rule is satisfied, then okay, my system is nonlinear system, or it is stable, the behavior is stable, or the behavior is unstable. So what do? We apply whatever we have learned in the linear system analysis, and then we further use it to find the stability of my nonlinear system. So for the stability analysis, we have talked about finding the eigenvalues, right? We have also discussed the graphical method in which we were plotting x dot with respect to x. And then if like for example, if this is x dot and this is x, and my behavior is something like this. So we discussed that, okay, for like here, the velocity is positive. So the path is going to be like this. Here the velocity is negative, so the path is going to be like this. Okay, so as we discussed, the path is going to be something like this. Here the path is going to be something like this. Here the path is going to be something like this. That is how we discussed about the stability of my fixed point. This was the graphical method. So here I came to know that, okay, this is a unstable fixed point and here it's a stable fixed point, right? So this is how we discussed for the graphical method. Now, for example, if I am not into going into the, because this graphical method, I can use up till some order of nonlinearity. However, if the order of nonlinearity increases, then I cannot plot this graph. So then what will I do? So the best way is that we go into the mathematical calculation. So there we got to know that, okay, if I take the fixed points, and then when I take the fixed points, if I linearize my system about that fixed point, and then if I try to find out the stability of that fixed point for that particular linear equation, then I'll get to know that, okay, whether my system is stable or whether my system is stable for that particular equilibrium point. And we used the concept of Jacobian also over here, right? Wherein we were linearizing the system, and then we were linearizing the system, and then upon linearization we were putting the equilibrium points into the Jacobian matrix, and then when we found out the eigenvalues of the Jacobian matrix, on the basis of the eigenvalues we could say that, okay, if my system is stable or if my system is unstable. Like if you remember, if the eigenvalues were all negative, we would say that the equilibrium point is stable. If the eigenvalues are all positive, the equilibrium point was unstable. If it was one positive, one negative, it was a saddle point. Likewise, we discussed. Okay. So once we have talked about the stability analysis, the question is that in the case of a dynamic response, how my system is going to behave. Now, see, for a linear system, it could either converge to a equilibrium point. All right. For a linear system, what are the possible response? It could have a equilibrium point, periodic response, right? But if I talk about a nonlinear system, now there are various parameters that play a very important role in case of a nonlinear system. So then in that case, if I talk about the response, there are different kind of possible responses that I can see. So first is definitely going to be an equilibrium point, because if my system is, dissipative in nature, so it is going to, if I'm going to give it some kind of a perturbation, it is going to converge to a particular equilibrium point, and definitely it is going to be a stable equilibrium point, right? So either it will converge to a stable equilibrium point, or it could diverge from an unstable equilibrium point, or if I'm starting the dynamics from the unstable equilibrium point without any perturbation from that particular point, then it will stay at that point. Then the response could be periodic, which means it could have a closed path, and a particular response is getting repeated after a particular period of time. It could have that response. Now, there could be a quasi-periodic response. You know what is a quasi-periodic response? For a quasi-periodic response, if we have two frequencies present in the system, omega 1 and omega 2, such that omega 1 and omega 2 are incommensurable, which means that the ratio of omega 1 and omega 2 is irrational. Incommensurable, or omega 1 by omega 2 is irrational, right? So in that case, quasi-periodic response is going to occur, right? And apart from quasi-periodic response, chaos can happen in a nonlinear system. Now you see, for the chaos, we studied that it's an aperiodic response. And how do we identify chaos, since we don't know if the response is actually chaotic or whether it is quasi-periodic? So what were we doing? We were actually using one of the property of a chaotic response, which was that it shows high sensitivity to initial condition, right? So what we were doing, we were giving a very small perturbation in the initial condition, and then we were using both the responses. We were plotting it in the same plot, and then we were checking how is the dynamic behavior. So we saw that up till a certain amount of time, the response was exactly the same. However, after some time, the response diverges from each other in such a way that once one response is at its peak, the other response is at its minimum point, right? So that is how we were characterizing chaos. And since chaos shows such high sensitivity towards initial condition, it should always be avoided in case of a dynamic response. So yeah. Hi, yeah. Apart from that, we had subharmonic and superharmonic response. Uh, yeah. So now the question is, what is a subharmonic and superharmonic response? So first, what is an harmonic response? So if I have a system such that it is having some forcing of frequency omega, right? And it has this damping present inside the system. So what is going to happen? My system is going to behave in a periodic fashion, and it is going to have a frequency which will be equal to the forcing frequency, right? That is what happens in a linear case. But in case of a nonlinear system, because of the presence of nonlinearities, my system is going to show a response which are not actually equivalent to the harmonic frequency, but actually equivalent to the, it's like integral times of that frequency, or it is the integer divided with that frequency. So for example, if I have an equation of the form, I write the form x double dot plus kx dot plus alpha x plus beta x cube f cos of omega t. Okay, I have something of this type, right? And then, and then for this equation, if I assume my x as a naught plus a1 cos of lambda t plus a2 sine of lambda t. Okay, here I don't assume that my lambda is already equivalent to omega. Okay, that I know for a linear system, but here I'll assume that it is not equal. So if you'll put this in the main equation, x, you can compute the x dot, x double dot, and everything, you'll get to know that the most obvious way of getting this value of lambda is equals to omega, which is actually the harmonic response, which is actually the harmonic response. However, there are other possible ways. Now you see, since there is a cubic nonlinearity present, you are going to see that there could be terms of cos 3 times of lambda t, there could be terms of sine 3 times of lambda t, and such types. Okay, so in that case, what is going to happen? We are going to have an equality like n lambda is equals to omega, right? Which implies lambda is equals to omega by n. Now this is what? This is known as the subharmonic response. When your response frequency, when your response frequency is actually some integer is divided with the forcing frequency, it is known as a subharmonic response. This is your subharmonic response. Okay, and in this case, your time period is going to be n times of the original time period. Similarly, if you have lambda is equal to n times of omega, it is a case of a superharmonic response, and here the time period is going to be t naught by n. Okay. Apart from this, if you are having a forced system, right, and your forcing frequency, like for example, let me add another slide. You have this as your forcing frequency. and this is your natural frequency. So now if your forcing frequency is equal to some like 1/3 of your natural frequency, then this case is known as superharmonic. Okay, then this is known as superharmonic. While if your this is 3 times, then this case is known as subharmonic. Now you see these two are actually different cases because here we are actually relating the response frequency with the forcing frequency. Here we are relating the response frequency with the forcing frequency, while here we are relating the forcing frequency with the natural frequency of the system, right? So in this case, my time period, right? My time period is going to be what? It is going to be for the superharmonic, it is going to be 3 times of T naught, where T naught is what? It's the time period which is corresponding to the natural frequency of the system. While in case of subharmonic, the time period is going to be 1/3 of the time period corresponding to the natural frequency of the system. Okay, I hope this is clear. Okay, now we talk about the solution of differential equations. Okay, we are done with finding out the differential equations. But now, when if we want to know that what is going to be the solution of my, okay, just a second, charger hai. Subin, do you have charger? Phone charge. Huh, thank you. I'll give you some time. Hmm? ये आईपैड नहीं चार्ज हुआ है, बहुत ज्यादा बैटरी ड्रेन आता है. Yeah, okay. There was some issue with the charging. Now it's done. Okay, so now, yeah. So now we were talking about the solution of nonlinear equations, right? Now we have got the nonlinear equation, and we have discussed about how do we talk about the stability and what are the possible solutions that can happen in a nonlinear system. But the question now is, how do I get the solution? Once I'll get the solution, then only I can actually talk about that how the system behavior is going to be, what are going to be the static characteristics, what are going to be the dynamic characteristics, right? So for that, we need to solve. Now, since we have a nonlinear equation, and if I want to have a closed form solution, it is very difficult. I'm not saying it's impossible, but it's very difficult. It requires a lot of mathematical calculations, a lot of assumptions, and many more things, right? So for a nonlinear system, just a second. So for a non-linear system, there is some issue in my writing. Okay. Okay, anyways. So for a non-linear system, finding a solution is difficult. So either we switch to the numerical method for finding the solution, or what do we do is we use some approximate analytical methods, which is like harmonic balance method, the Linson Poincaré method, method of averaging, and the method of multiple scales that we can use in order to find out the approximate analytical solution. Now, if you have studied well that what are these approximate analytical solution, you people must have realized that these methods, though they are good for getting the solution, it is not actually a reliable way, right? Because it can get me a solution only under certain kind of an assumption. Like for example, if I assume that my steady state response is going to be periodic, then I can use any of these methods. Like for the harmonic balance method, if like we used it in this here, we assumed a harmonic solution, but we assume that the solution is going to be of this format only. But is it true? In the transient state, is it true? No, definitely it isn't. So then what do we do in that case? In that case, we switch to the numerical method. However, if my system is to be used in a static state, sorry, not, yeah, static state or a steady state, right? For that, I can definitely rely on these approximate analytical solutions because it is going to give me a very reliable closed form solution. Or if my oscillation amplitude is less, so that it could be covered in a linear zone or a slightly non-linear zone, then we can use these approximate analytical methods. However, if my system is highly nonlinear and it is very difficult to obtain an approximate analytical solution and I have to consider transient response as well, so then I would switch to a numerical method, right? So for the numerical method, we have various ways, right? Various numerical methods in order to find the solution of my system, right? Like we had ODE45 or we had the RK4 method. ODE45 is the inbuilt MATLAB function. We discussed about the RK4 method, we discussed about the Euler method, and we also discussed about how RK4 method is better than Euler method, right? And so we came to know that, okay, numerical solution is a good way of us. But then we also discussed an example wherein we saw that though my Euler method is a way of getting the solution, but the Euler method could also give absurd solutions depending upon how much of the step size we are choosing. So choice of the step size, it also plays a very important role, and it depends wholly on my nonlinear equation. If my nonlinear equation is stiff, then definitely the solution of my system would depend upon the choice of the step size, right? And for that, MATLAB again has a built-in function which is OD15S, which is used for specific stiff kind of nonlinear equations. And I suppose that we have discussed a lot about the numerical solutions and how if we have a equation of motion, how should we write the code in MATLAB to get the numerical solution. And we also did discussed about one example wherein we used the RK4 method to compute the solution like manually. So I think this is clear, right? So this is what we discussed about finding the solution, right? Now, okay, I found out the solution, but then how to analyze it? But then how to analyze it, right? So first thing is we get the time response, wherein we get the plot of my response with respect to time, right? I have a time and then I plot the response with respect to time. Second is my phase plot, where I plot the displacement versus velocity, right? So in that, I get to know like the some of the characteristics which I am not able to recognize in the time response. Like for example, if my response is periodic, I cannot exactly see it in the time response. Though in the time response, maybe I can see that it is periodic, but when I plot the phase plot, I can see that there is a, a very thick line in the phase plot which shows that though the response seems periodic in the time response, but in the phase plot it is not exactly periodic. It could be quasi-periodic. It could be quasi-periodic. And then if I have my chaotic response, then also I can see it in the phase plot and see that okay, the phase plot is filled, uh, like for example in the periodic case we have a line, for the quasi-periodic we have multiple, donut kind of a shape which is filled in between. And for the chaotic response, we have a filled phase plot, right? So that way, the phase plot is essential in order to know the dynamic characteristic. Then we have jump up and the jump down, which we discussed in case of the amplitude frequency response, if you remember, wherein we had the amplitude frequency response, for a linear system, it was different. For the linear system, we had the response in such a way that at my natural frequency, we had an infinite amount of amplitude, right? But just a second. Yeah. So for my linear system, the response was something like I had the amplitude, I had the frequency, and the response was something like this. But for the nonlinear system, this was not true. For the nonlinear system, we could see either a bend in this direction or a bend in this direction. Okay, it could be something like this or it could be something like this, right? Now, because of such kind of a structure, we saw the jump up and jump down phenomena, right? With the frequency sweep, like if I sweep the frequency, instead of following the actual path, it actually jumps down like this instead of following this path. Why? Because this is the unstable branch. And we discussed yesterday that this branch is essentially an unstable branch, and at these 2 points, there are dynamic saddle node bifurcation that is happening, right? When we talk about the subharmonic and superharmonic response, we have already discussed about it, that what is a subharmonic and superharmonic response. Depending upon if how do I relate the frequency of oscillation with the forcing frequency, and if we relate the frequency of my forcing function with the natural frequency of the system. Okay. Then we also discussed about the numerical techniques which could be useful, right, for differentiation, integration, for finding out the roots. For integration, we exactly know what is the use of a numerical method for integration, which is our RK4 method, which is for solving ODE. What are we doing? We're actually integrating with respect to time only, no? Then there is integration function also, int, which could be used in order to integrate with respect to the particular variable only. For differentiation also we can use it, and for finding out the roots, which is also one of the important things for us, because for a nonlinear system, we have a nonlinear equilibrium equation, right? And if I have a nonlinear equilibrium equation, how do I solve it to find the roots? Or the roots are only going to give me the equilibrium points. So how do I find my equilibrium points if I have a nonlinear equation? If it is mathematically difficult, then I use the numerical methods for finding out the roots, which is, the Newton-Raphson method, or we have the bisection method, etc., etc. We have discussed very elaborately about it. Then coming on to, we discussed about the types of damping, where we saw that there was Rayleigh damping, Coulomb damping, right? Then we had this friction, and these kind of a damping could be present in the system. And then we came to know that okay, for a nonlinear system we could have viscoelastic behavior, right, wherein there was amalgamation of the elastic plus the viscous behavior, right? Then we studied about the modal analysis, In the modal analysis, what were we doing? We were decoupling the equation for multiple degree of freedom system, right? We were decoupling the equation because we were getting the different frequencies that were present in the system. Like for a single spring mass system, we know that the frequency is going to be under root k by m. But if I have two spring mass system, the frequencies are not going to be k by m, under root k by n, and under root k by m for both of them. It will be different. It will be, as I remember, it would be, one would be 2k by m under root, and one will be k by 2m, right? And if we use these frequencies, we can actually get the eigen directions. And if I get the eigen directions, then if you remember that we used a concept of how to find out the stability for a 2 degree of freedom system, where we came to know that, okay, if I get two independent solution, if I get two independent solution, then I can write other solution as linear combination of both. So modal analysis is essentially important in order to find out the exact solution. Then we studied about the bifurcation, the bifurcation with the variation of parameter, the equilibrium points were changing, number of equilibrium points were changing, the stability behavior of the equilibrium points were changing. That is what bifurcation was telling about. Then we further extended the concept of bifurcation. How? By using the dynamic bifurcations, right? Wherein what we saw in the jump phenomena, that there was two SN bifurcation that were occurring, and those were dynamic SN bifurcation, because there we were not discussing about the equilibrium point, but rather we were discussing about the stable or unstable amplitudes of periodic response, right? So bifurcation was all about that. And if I talk about bifurcation, just right, there was static, there was dynamic, we had SN bifurcation, we had pitchfork bifurcation, then we had transcritical bifurcation, right? In pitchfork, we had subcritical and supercritical. Yeah, we had subcritical and supercritical pitchfork bifurcations. Apart from that, we have also seen the period doubling bifurcation. You remember the period doubling bifurcation, wherein the period of the time period was actually getting doubled. Then we had hop bifurcation, right? And these were the types of bifurcation we discussed. And anyways, this SN, pitchfork, and transcritical bifurcation, they were there for the static as well as the dynamic cases. Okay. So bifurcation actually took a lot of time. Bifurcation is one of the very important thing in case of a nonlinear system, because it is very essential for us to know that how our system dynamics is changing with respect to a particular parameter. And bifurcation is happening in case of a nonlinear system because of the non-monotonic response. Right, because in case of a monotonic response, there could be an equilibrium point which would either increase with increase of the parameter, or it would just decrease with the decrease of parameter. But in case of a nonlinear system, we can see that the number of equilibrium points are changing with the parameter change. The stability of the equilibrium point is changing with the change of parameter. The type of bifurcation is changing with respect to the change of parameter. So that is because of the non-monotonic response, and that is because of the this is one of the very important characteristic of a nonlinear system, right? Then we discussed about the types of fixed point, types of fixed point, like we have stable, unstable, center, saddle, likewise we had etc. We had many types of the fixed point, which we discussed about, and we had a figure also wherein we plot the figure between the trace of the eigenvalues and the determinant of the eigenvalue, and then we get to know that okay, if the eigenvalue trace and determinant lies in this region, then it is going to be stable, or it is going to be a saddle, or it is going to be a center, etc. Then we discussed about the basin of attraction. We discussed in the last week's live session only. So I hope this is clear. We don't have to discuss about the basin of attraction again. Then we talked about a parametrically excited system. We had a force excited system wherein or externally excited system, like that in case of a spring mass system with a forcing present in it. What was happening there? So what was essentially happening was that we had a forcing function which was externally providing a force to my system, right? Which was externally providing a force to my system. But in case of a parametrically excited system, like the example which was discussed in the your classes, which was that of a beam, right? Wherein the forcing was in one direction, but your movement was in the lateral direction, right? Because of that lateral direction, it was actually having a parametrically excited system. Now, that is a different case. What if I talk about a soft material, like we discussed about a pneumatic artificial muscle yesterday? Right? So in case of a pneumatic artificial muscle, we got to know that, okay, the stiffness of my material actually depends on what? It actually depends on the air pressure that is inside that pneumatic artificial muscle. Now, if that air pressure is varied, right, with respect to time in a sinusoidal or cos function way, then it is a parametrically excited system. Because in a parametrically excited system, essentially the parameter is varied. The parameter is varied with time and it shows a periodic nature. Then we say that, okay, it's a parametrically excited system. Okay, so for a pneumatic artificial muscle, if the air pressure is given in a sinusoidal way, then it's a parametrically excited system. Now, for a parametrically excited system, the resonance theory is different as compared to the externally excited system, because for the externally excited system, the resonance theory says that if my forcing frequency is equal to the natural frequency of the system, then okay, I'm going to see a resonance condition, the amplitude is going to be high, right? But in case of a parametrically excited system, that is not the case. In case of a parametrically excited system, there could be two cases, which could be a principal parametric resonance and the other could be a combination resonance. So in case of a principal parametric resonance, the forcing frequency could be n times of any of the frequency, natural frequency that is present in the system. Well, in case of the combination resonance, it could be the sum or difference of the natural frequency that are present inside the system. Then we discussed about the flow K theory. Now, see, when we discussed about the stability for a equilibrium point, we were actually finding out the eigenvalues, or we were linearizing the system and then finding out the eigenvalue, or we were finding the eigenvalue of the Jacobian matrix. And then on the basis of the eigenvalues, we were saying that if the particular equilibrium point is stable or unstable, etc. What about in case of a parametrically excited system? Now, I cannot deal with a parametrically excited system in the same way as I deal with a externally excited system. So in case of a parametrically excited system, flow K theory was introduced. Now, flow K theory was helpful in order to predict whether the response that my system is showing, it is stable or unstable. That's fine. But the use of flow K theory in order to find out the stability of a periodic response, that is a very important application of the flow K theory. Because you see, I have also discussed by taking an example in one of my live session that how using the flow K theory, I can talk about the stability of my periodic solution. Whether my periodic solution is essentially stable or unstable will depend upon the values of my flow K multiplier, right? If my flow K multiplier, it lies inside the unit circle, then my periodic response is stable, while if it lies outside the unit circle, my periodic response is unstable, right? So that way it is very helpful. Now, okay, then we also discussed about one of the very important thing that we talk about in case of a nonlinear system is a limit cycle, right? Now, if you remember that for a spring mass system, if I have a periodic response, right? Like if I have a spring, I have and a mass attached to it. and I give some perturbation to the spring, what is going to happen? My mass is going to oscillate with some amplitude and frequency. The frequency is definitely going to be the natural frequency of the system, and the amplitude will depend upon what initial condition I'm giving. Now, if I change the initial condition by a small amount or either by a large amount, anyways, the amplitude is going to change. The amplitude is not going to remain the same. The frequency is going to be the same, right? So that is a periodic response. But then what is a limit cycle? So, a limit cycle is essentially an isolated periodic orbit. In case of a spring mass system, there were multiple periodic orbits. It was not isolated. Now, when I say isolated periodic orbit, in the phase plane, I have only one stable periodic orbit. So, no matter what is my initial condition given to the system will always converge to that one isolated periodic orbit, right? So, essentially, it's a stable periodic orbit. In case of a spring mass system, the periodic orbit, it is neutrally stable, right? It is neutrally stable. Neither my system is going to converge, neither my system is going to diverge. If I change the initial condition, it is not going to follow that path again. While in case of a limit cycle, it's a stable, isolated periodic orbit, right? So if such kind of a limit cycle is present, then how do we deal with it? We have discussed. And limit cycle, I've also told earlier also that limit cycle is a kind of an oscillation, isolated periodic orbit, which is present in the nature very commonly. Like for example, the beating of a heart could be considered as that of a limit cycle because it always oscillates at a particular frequency and has a particular amplitude, right? So it's a kind of a limit cycle. Now, then we talk about the existence of a closed orbit, and we discussed about that how do we know that whether the closed orbit is going to exist for a particular system or not. So that was done by using the gradient system, Dirac criteria, and the Lyapunov function. For the use of this, we could tell about the existence of the closed orbit. Then we talked about the stability and bifurcation of periodic response. Bifurcation of periodic response, like we discussed for the jump phenomena case, that there were two saddle node bifurcations that were happening, and those two saddle node bifurcations were actually dynamic bifurcation for that of a periodic response, because there we were having amplitude, a stable, two stable and one unstable amplitude. And then we discussed about the stability of the periodic response, which was based on the Floquet theory, which I have discussed earlier also, and I've taken an example also. If you have any doubt, you can go to that particular week's recording. Then we discussed about the numerical techniques for differentiation, integration, finding the roots, and solving differential equations. This we have discussed a lot and will not be discussing again. Then we discussed about the logistic maps, wherein the logistic map was actually a population growth model, where then this was a discrete model, if you remember. Up till now, we discussed about only continuous model. Only logistic map was the kind of equation for which we had a discrete model where the population size at n plus 1th iteration would depend upon the nth iteration, right? And we saw that logistic map shows with the variation of the parameter r, it shows period doubling bifurcation, and which leads to chaos, right? And then we discussed about the Poincare section and Lyapunov exponent. So, the reason for Poincare section was that if I have a chaotic response in my phase plot, right? If I have a chaotic response, then for that chaotic response, how will I know that what is the inside behavior of the system? See, I know it's a chaotic response. It's an aperiodic response. I can see it in the phase plot. I can see it in the uh, this time response as well. But, there is one property of the chaotic response, that it is always bounded. It never goes to infinity. Even if in the phase plot, if you'll plot the chaotic response, you'll see that it is always bounded. It is always bounded. Like for example, if I consider something like this, and this is my phase plot. So you'll see for the chaos, I have this thing filled. Maybe I should do it like, Yeah, this is going to be my phase plot for the chaotic response. I'm just taking an example because this kind of behavior I got for my research work. So this is going to be the phase plot, right? But you see, okay, in between it is all filled up with points and I don't know how the behavior is. But if you see, it is always bounded. There is a boundary and it is never crossing that boundary. So what is happening in the inside the system that it is never crossing the boundary, right? So then when we plot the Poincare section, and in Poincare section, what do we do is we try to reduce one of the dimension of the system, right? Usually chaos is possible only for a three-dimensional system. And if I reduce one dimension of the system and if I try to find out how reducing that one dimension is going to show me the response of the system, so I'll get to know that there is some kind of a, you know, this attractor present inside the system. There is some kind of an attractor that presents inside the system, right? And this attractor we call as strange attractor. We call it as a strange attractor, right? So that is why Poincare section is essential in order to find out that how is my behavior of the system if I reduce one dimension. Like for example, if I want to find out the Poincare section of a periodic response, this is a periodic response, then this Poincare section is going to be nothing but a point. Because if I try to cut my response after an interval of time, I will see that it always comes to that particular point, and hence there's only going to be one point for the periodic response. Now, since chaos is an aperiodic behavior, so it is going to show the presence of a strange attractor. And then we have a Lyapunov exponent, which is essentially used to, measure the rate of convergence or divergence, measure rate of convergence or divergence. So if my Lyapunov exponent is positive, I say that my response is chaotic. If it is negative, I say that my response is non-chaotic. Now, you see that we only discussed about the graphical tools in order to find out the behavior of chaos, but we should have a quantitative value to characterize chaos and non-chaotic response, and that is what the Lyapunov exponent does. And coming on to what we discussed in the last 3 weeks lecture, it was the vibration reduction techniques and why vibration absorbers or vibration reduction techniques are required, right? We discussed about that, okay, if a machine is operating in a factory and if that machine is having some kind of a vibration, which may be due to, because of the eccentricity of the mass that is present in the system or any other reason, then that kind of a vibration needs to be reduced, right? Or it should be absorbed, because that kind of a vibration can actually affect my system as well. It can actually cause the transfer of the vibration onto the floor. It could cause the, problem to the sensors that are present on the machine, and it definitely reduces the efficiency as well. So then vibration reduction and vibration absorber techniques were discussed, which could be useful in order to reduce the effect of vibration, in order to increase the efficiency of my system. And usually flexible materials like rubber are used in order to get the vibration reduction or vibration absorption. And then we discussed about, electroactive polymers or MR based elastomers that could be used for the active control of the vibration absorber, right? Because there, by the change of the electric field or the magnetic field, we can actually change the properties, or we can actually change the shape and size of my system. I can change the stiffness of my system. I can change the viscosity of my system. So that would be helpful for us to, increase the range in which my particular absorber that I have designed could work, right? So that is what we discussed. And since these MR elastomers and the electroactive polymers, they are essentially flexible materials, they uh, needs to be governed by the nonlinear dynamics. Then we had flexible nonlinear system. Then we had excited cantilever beams and piezoelectric energy harvesters, applications of nonlinear dynamics, and then we talked about chaos and its control. So for the flexible system, what did we do? We actually discussed about how we can use the flexible system for different kind of application. Like it was discussed that how it could be used for energy harvesters, wherein we could have a cantilever beam which is fixed at one of an end, and if we apply a piezoelectric sensor over here, then due to the rotation of this cantilever beam, the piezoelectric, the piezoelectric effect, that if there is the change of the dimension of my piezoelectric material, it will cause the generation of voltage across it, and that voltage could then be taken in, right? It could be taken in, and that could be used as a energy generation purpose, right? Then we talked about application of nonlinear dynamics, which was specifically in case of a manufacturing process where we had chattering, which was the unwanted vibration in the manufacturing process, like in case of rolling or milling, right? In case of rolling or milling, wherein that chattering was happening due to many reasons, like problem with the fixtures due to inaccurate readings and you know tool wear and everything, and it could further lead to tool wear. It could also lead to inaccuracy of the workpiece that I make. It could also lead to catastrophic failure if the frequency range is very high. Then we discussed about the octaves also, right? And if it is in the fifth octave, the chattering frequency is in the fifth octave, it would lead to catastrophic failure also, right? And then we discussed about chaos and its control, wherein how chaos is affecting the system and how can we control it. Essentially, we were controlling it either through stabilization or synchronization. In the stabilization, we had two ways. We could actually make it follow a particular tracking signal, or we can make it settle down to any of the unstable or stable equilibrium point. Or the second way was synchronization, in which we could synchronize the two, three vibrations that were happening in the system. And then the control was possible because of the controllers like PID controller. Then we had the adaptive controller, fuzzy logic, neural network based. These types of a controller could be used to apply the control strategy into the system. Apart from that, there were two possible ways, which was one of the feed forward control and there was a feedback control. Anyways, the feedback controller is the best for us because using a feedback controller, what we can do is we can actually calculate the error inside the system and we can decide how much input is required by the system. So if this is the output response of the system and we apply a controller over here, we take the feedback. We take the feedback like the output, if we take it and we feed it inside the controller. So my controller is capable of, deciding that how much of the input is required. So what does the controller do? It takes up the feedback. It knows what the reference signal is. I've already given it the input of what the reference signal should be. So on the basis of the reference signal and the feedback that it is getting, it is going to decide that how much input is required, how much input is required, and that input would further lead to the required response. So you see, in this course, what we have studied about is that how do I get a nonlinear system? How do we derive the nonlinear system? How do we check whether the system is linear or nonlinear? Once I get a nonlinear system, how do I find its solution? What are its characteristics? What are going to be its steady state characteristics, like the number of equilibrium points, and then what is going to be the stability of the equilibrium point, and how do we find out the basin of attraction. And for the dynamic cases, we discussed about what are the possible responses that can happen in a nonlinear system. Once I get a probable response, how do I know about that whether the response is chaotic or non-chaotic by using the Poincare map or the Lyapunov exponent? And once I get those, how can I use my nonlinear system for different kind of application, like for a manufacturing process, for energy harvesting, for vibration reduction techniques? And then if I have chaos, how do I try to control it? Because you see, chaos is inevitable in case of a nonlinear system. It is definitely going to happen in a system in any way. So if the chaos is present inside the system, then how do we actually reduce the chaos, or how do we actually neglect, uh, you know, my system from going into the chaotic response. So I think the presentation, yeah. Okay, so this was it for the today's extra session. It was of 1 hour only. So I thought that I'll discuss. I think there is no doubt. If there is any kind of a doubt, you can ask. If there is no doubt, we can end the session. And this was it for the live sessions for the course nonlinear vibration. And we are already done with it. And I hope that this course was able to make you interested into the nonlinear vibrations, how nonlinear vibrations are happening, how can we actually work on nonlinear vibrations and everything, and how do we actually deal with a nonlinear system. Yeah. So, okay, we'll end this live session. And if in case you have any doubt, you can contact me on my email ID, which is rashi_2121 me13@iitb.ac.in, and I'll be happy to respond. So all the best for your exams. And now I'll end the live session. Thank you very much.